So hopefully you tried out this innocuous little problem that we mentioned, the Bessel's equation with J0 as the solution, and tried to integrate it yourself using methods that we have talked about. And if you evaluate the accuracy of the solutions you were getting, hopefully you try to do that by comparing the solution to the J0 function. Although the solution that you have numerically computed may look perfectly smooth and reasonable in some way, maybe you were finding that it doesn't agree with the J0 solution, which is the solution that we expect to get. And so you may be wondering what is going on in this simple little problem. Why is this method misbehaving? Why is it not giving the solution that we claimed to be the solution to the original differential equation? And so this requires a little further thought. And so if we actually look at the problem that was given and sort of abstract out the main idea, we are in this case looking at numerical solution of second order ODE, where the initial point from which we are carrying out the integration is not a regular point, is not a simple point, but it's a singular point. It's a regular singular point of the differential equation. And so because it is a regular singular point of the differential equation, x equal to 0 is a regular singular point of the differential equation, the Bessel's differential equation. So it's something that we have to recognize and pay attention to, and we will see it's very simple what is going on, and we can fix it in a simple way, but we need to recognize that we are starting integration from a regular singular point. And this is not to say that this is a contrived case. In a lot of engineering and science applications, we are dealing with a behavior where we need to integrate the solution from a singular point or across singular points, and therefore we need to know about how to treat the behavior near such points. So let's look at the analysis that we need to do to fix this problem that we encountered. So given the initial value problem, y double prime equals some function capital F of y prime, and x, and the two initial conditions, we are interested in the solution when x equals x0 is a regular singular point. So it's not an ordinary point, but it's a singular point. Of course, well, how will we do this? Of course, we are going to use the method that we have talked about before, that we're going to rewrite it as a system of first order ODEs. And so everything that we have talked about before, we do that. And so we recast the problem, the second order equation, as a system of two first order equations, y prime equals this right hand side capital F, involving the functions f1 and f2, where the components of f1 and f2 are simply f1 is equals y2, and f2 equals this right hand side function associated with the differential equation that we were given. So that is what we do, and this is probably what you programmed, but the behavior didn't work out. This numerical solution didn't work out. And the reason it didn't work out is that the differential equation goes here, and this f2 function is not well behaved if we don't pay attention to it. And so what we need to do is near the regular singular point, we need to use analytic behavior of the solution to the differential equation. Otherwise, we are not describing the correct behavior of this differential equation near this regular singular point. And so once we do describe the correct behavior numerically, we will obtain the correct solution. And so we will mention how we do that in a step, but once we have recognized that f2, we need to look at its behavior near the singular point, then we can program a little condition in our numerical solution. We can say that if we are close enough to this singular point, then an expression, an analytic expression for f2 is used, which is better behaved in the vicinity of this singular point. And then once we are away from the singular point, we just use the given differential equation without any modification elsewhere, and so on. So the region where a simplified expression or a particular expression for f2 gets used can be very close to x equals x naught. In terms of practical implementation, you can decide on some threshold. You can say that if that difference numerically is say 10 to the minus 7 or some small number times the x naught, so when it's really close, we can do an approximation to it, which expresses the correct behavior near the singular point. All right, so let's illustrate all this on the differential equation that we talked about. So Bessel's differential equation, J0, the ODE is written over here, and so we are rewriting the differential equation to obtain the second derivative. Second derivative is given in terms of, this is the f2 function for the particular differential equation, and notice that J0 is a well-behaved function. These are the two initial conditions. J0 of 0 is 1 and J0 prime at 0 is equal to 0. So if you think about what is happening over here, this is going to 1 for small x, and the numerator here is vanishing and denominator is also vanishing. So J0 double prime for small x is not well defined unless we actually take the proper limit. Numerator is vanishing, denominator is vanishing. They're both vanishing at the same rate, and therefore this ratio is not going to 0. If you don't take this explicitly into account or simply program it, computer is going to make its own treatment. J0 prime is not blowing up, it is small. So that small number divided by this small number is a finite number, and the computer, depending on the precision that you have, this ratio might not turn out to be well behaved, may magnify round off errors and so on, and then cause problems. The solution might not work out. So we can recognize the fact that this first term, the numerator, is vanishing, and work this ratio out analytically and use that relationship. So that is what we're going to do. So J0 function is that linearly independent solution of Bessel's ODE which satisfies these two conditions. And for small x, because of these two initial conditions, J0 starts with 1, and then because the slope is 0, it doesn't have a linear term. It starts 1 plus a quadratic term plus order x cubed, and so given this expression where the coefficient a so far is unknown, we can obtain expressions for the first and second derivatives, and so once we have these expressions, we can substitute that in the right hand side here to evaluate f2 for small x, and so J0 double prime, this is the exact result, and then we have substituted the expansions for J0 prime and J0. This is the expansion for J0 prime. This is the expansion for J0 itself. And so if we ask, well, what is going to happen to this right hand side for small x, we can see that for small x, it becomes minus times in the bracket 2 capital A plus 1. That's the limiting behavior. So depending on the coefficient A, this thing achieves some value which obviously depends on A. And so that is what we need to know, what this A is. And so then the question is, what determines A? Well, A is determined by the differential equation, because after all, the solution, this is the initial condition, and we need the differential equation to define the solution starting from that initial condition. So all we need to do is substitute these expansions in the differential equation, and so that is what we are doing here. X square is this x square, J0 double prime is represented by this expansion in the curly brackets, x is this x, J0 prime expansion is substituted here, x square is x square, and this is the expansion of J0. And once we write it, you can see that at leading order, in terms of order x square, the coefficient is 2a, 2a, and 1. So it's total 4a plus 1. And if this equation has to be satisfied for small x, then this coefficient must vanish. And of course, this is a standard method which you can use to obtain a series expansion for the solution. And so if you go to higher order, do the same thing by putting coefficients of order x cubed, order x4, and so on equal to 0, you'll get more and more terms in terms of the series expansion. Here it's enough to obtain just the first term, this quadratic term. And so setting this equal to 0 gives us a value of a equals minus a quarter. And once we have this value, we can substitute that in the right hand side. And so then we get that the right hand side, or J0 double prime at 0, is equal to minus a half. And so it has a well-behaved value of -0.5, which is what we need to start from. And once we say that, say when x is less than some 10 to the -7 or some threshold that you choose, we can say that j0 double prime is equal to -0.5. And when it's bigger than that threshold for x, then we can use the full expression, this expression, where this, of course, since we are writing this as a system, we can evaluate this right hand side. We don't need to know j0 itself. It's a numerical approximation at every point that we are obtaining that is available, and we can simply use it. So this little investigation of the behavior of the solution near a singular point, in this case we illustrated it for the Bessel function equation, but analysis called Frobenius method, or power series expansion of the solution near a singular point, in general can be used to find out what is the behavior for a particular equation, and thereby one can build in a particular limiting behavior near the singular point to treat the problem that one is facing. So this fixes the difficulty that we have in this simple illustration, and now let's apply it to the integration and see what results we obtain.